In this lesson today, we're looking at going through some examples and determining the area between curves. So in this first example, we're asked to find the area of the region bounded by the parabola y equals x squared and the line y equals 2x. So pretty straightforward. If we put this in, we've got x squared and we have 2x. And if we draw that, it's pretty easy to see that these two functions only have one area that's bound between them. So x, y, we've got our y equals 2x, and we've got y equals x squared, and we've got our area that's bound. So we can say f of x is equal to 2x, g of x is equal to x squared, and our difference function will be f of x take g of x, which will be 2x take x squared. Now, these intersection points are really important. You can solve them by hand, or you can do that on your graphics calculator. I will solve on my graphics calculator. So the intersection will be, we have our first intersection point when x equals to 0, and the second one when x is equal to 2. So that means our area is the integral between 2 and 0 of our difference function, which is 2x take x squared with respect to x. Now the rest of this process is pretty straightforward. The integral of 2x is 2x squared on 2. The integral of x squared is x cubed on 3. And we're between 2 and 0. So that will be x squared take 1/3 x cubed between 2 and 0. So when we sub this in, we've got 2 squared take 1/3 times 2 cubed, and subtract 0, because 0 squared and 0 cubed is both 0. So we have 4 subtract 8 on 3 units squared. And as 4 is 12 on 3, we can say we have 4/3 units squared as our final answer. So let's check this. G-solve. We can find the integral. We can use the intersects. So we got 0 and 2, and we get 1.3 recurrent, which is 4/3. Okay, so we'll look at the second example. Calculate the area of the region enclosed by curves y is equal to x squared plus 1 and y is equal to 4 take x squared. So we'll do the same thing. We'll start by sketching them. Okay, so pretty straightforward. We've got x squared plus 1, which is just an x squared function moved up 1. So we'll say this is f of x. We've got our 4 take x squared, which is an inverted x squared function, shifted up 4. So here's our g of x, which is 4 take x squared. We've got our area here, and again, we need to make sure we work out these intersection points. So our intersection points will be negative 1.22 and 1.22. Now, I'm going to do this by hand just so you can see. So the intersection will occur when f of x is equal to g of x. So we've got x squared plus 1 is equal to 4 take x squared. And we can add x squared to both sides, so we've got 2x squared plus 1 is equal to 4, subtract 1, and we've got 2x squared is equal to 3. So x squared is equal to 3 on 2, and therefore x is equal to plus or minus the square root of 3 on 2. Okay, so that's our intersection. Our intersection is square root of 3 on 2 negative and square root of 3 on 2 positive. Now we also have these two important points which are limits or boundaries, and they are -1 and 1. So that means that the area that we're truly trying to calculate doesn't meet the intersect, so we don't have to worry about them. So if we define our difference function in this case, I will say it's g of x, subtract f of x, because g of x is above f of x in that section. Then it will be 4 take x squared, take x squared plus 1, which will be 3 take 2x squared. So our area will be between 1 and negative 1 of 3 take 2x squared with respect to x. So we have 3x take 2x cubed on 3 between 1 and negative 1. And therefore we have 3 times 1 subtract 2 times 1 cubed on 3 subtract 3 times negative 1 subtract 2 times negative 1 cubed on 3. So that is, we have 3 take 2/3 and we have negative 3 plus 2/3. So we end up with 9/3 take 2/3, which is 7/3 times 2, and we've got 14/3 units squared. Okay, so nice and straightforward. The next one, we're looking at the area of the region enclosed by the graphs x cubed and x. So if we go back and we put in our two equations, we have x cubed and we have x. We see that if we zoom in, let's go -2 to 2 and -2 to 2, and we sketch this again. Then we've got two boundaries. We've got a negative section and a positive section. So I'll quickly sketch this. We'll say the f of x, and that's x cubed. This is g of x, which is x. Then we've got two sections defined by 3 intersects. So g solve intersect, and we have -1, 0, and 1. -1, 0, and 1, which are our important points. Now, if we say our difference function is g of x subtract f of x, then we will have x take x cubed. And therefore, as we're looking at g of x being the top function, this will be a negative section and this will be a positive. So our area will be the integral between -1 and 0. I flipped these limits because it was a negative and we want it to be positive. So this is x take x cubed with respect to x, and we're going to subtract the integral between 1 and 0 of x take x cubed. So this is x squared on 2 take x to the power of 4 on 4, -1 and 0, and we're going to subtract x squared on 2 take x to the power of 4 on 4 between 1 and 0. So we have 1/2 subtract 1/4, and here we will have, realizing now that this should have been a addition the whole way through, and so that means we should have 1/2 subtract 1/4, and so we have 1/4 plus 1/4, and we end up with 1/2 units squared. Let's check this with our integral intersect calculation. So we've got our first intersect and the last. The integral is 0, but the signed area is 0.5, which is what we calculated. Okay, so next example, the sketch is already done for us. We just have to find the area of the shaded region. So these two intersect points are quite important. So it's when sine is equal to cos. So we have sine x is equal to cos x. Divide both sides by cos x. So we have tan x is equal to 1. And x is equal to arctan of 1. So we end up with pi on 4 being the acute angle that we're talking about. So this one here is pi on 4. This one will have to be in quadrant 3 will be pi on 4 into that section, which will make it 5 pi on 4. So this will be 5 pi on 4. So that means that our area will be the integral between 5 pi on 4 and pi on 4 of the difference function. Because for our region sine x is above cos x, we'll say our difference function is sine x take cos x. So the integral of sine x is negative cos x, and the integral of cos x is sine x. and we're working between 5 pi on 4 and pi on 4. So we have negative cos 5 pi on 4 subtract sine 5 pi on 4, and we're subtracting negative cos pi on 4 and take away sine pi on 4. So negative cos 5 pi on 4, cos is always going to be negative in this section. So it's just the same as saying cos pi on 4. And sine pi on 4 in this section is also always going to be negative. So that's the same as saying sine pi on 4. So in each of these cases, the negatives cancel out. And here we have negative cos pi on 4 takes sine pi on 4, which are unchanged. Now cos pi on 4 is root 2 on 2. Sine pi on 4 is root 2 on 2. And here we have negative root 2 on 2, take away root 2 on 2. So these two sections are equivalent, and so that gives us 2 root 2 on 2, or root 2. Root 2 plus root 2 is 2 root 2 units squared. So our last example, we're looking at finding the positive area between these two sections. So again, this intersect here is going to be really important. And that will occur when cos x is equal to sine 2x. Now, hopefully you can remember your double angle formulas. If not, they're on your formula sheet. Sine 2x is the same as 2 sine x cos x. And so when we cancel that, we end up with 1 is equal to 2 sine x. And therefore sine x is equal to 1/2. And if we're looking to solve sine x is equal to 1/2, we have two possible solutions. And our acute angle, which is arcsine of 1/2, will be pi on 6. So it's pi on 6 here, pi on 6 there. And our two solutions are x1 is pi on 6 and x2 is 5 pi on 6. Now, this one won't matter because it's outside the bounds. We can see that that upper limit is pi on 2. So it's this one here, pi on 6, that's important. Now, if we say our difference function, we'll let cos x be first. So cos x subtract sine 2x means we end up with a positive section here and a negative section here. And so that means our area is between pi on 6 and 0. We have cos x take sine 2x with respect to x. And then we can add on the integral between pi on 6 and pi on 2. We can see we flip those limits in order to make that positive. And we have cos x takes sine 2x with respect to x. Now all we have to do is calculate the integral. So integral of cos x is sine x. The integral of negative sine 2x is positive 1/2 cos 2x. And we're between pi on 6 and 0. And then we can add on the integral between sine x and 1/2 cos 2x between pi on 6 and pi on 2. So when we sub in pi on 6, we've got sine pi on 6, and we add on 1/2 cos pi on 3. So 2 times pi on 6 is pi on 3. Subtract sine 0 and 1/2 cos 0, and then we add on sine pi on 6 plus 1/2 cos pi on 3, and we subtract sine pi on 2 and 1/2 cos of pi. So sine pi on 6 is simply 1/2, and we've got 1/2 of cos pi on 3, which is 1/2. That means we've got a quarter. Subtract sine 0, which is 0, plus 1/2 of 1, which which is 1/2. And we have the same thing as the first, so we've got 1/2 plus 1/4, and subtract sine pi on 2, which is 1, and 1/2 cos pi, which is -1/2. So we have 3/4, subtract 1/2 plus 3/4, subtract 1/2, means we have 3 on 2, subtract 1, which is 1/2 unit squared. So that concludes the examples on finding the area between curves using integral calculus and difference functions. Obviously, the process is straightforward. Your process may differ slightly, so you may focus on sketching the difference functions. That's fine as long as your process makes sense and it's repeatable. Okay, thank you for listening.